All right, we're gonna go through this washer. Sometimes it's known as VMW, that they've been making this washer for a few years now. And VMW stands for vertical module washer, just the drive system. Back in the day, most washing machines had transmissions, and I remember back in the, I think it was the 80s, Sears came out with a washer called the World Washer, and it had the same plastic drive system that these machines have now. And that World Washer, to be honest with you, it was a Whirlpool design just like this washer is, and the top of the washer, even the control, not the control panel, but the actual top of the washer was plastic. Not the lid, but the actual top of the washer was plastic. And they had these plastic gears for the drive system. And everybody laughed because back then in the 80s, Sears had this big, huge transmission. I mean, it was literally this big with a shaft that long. And it was built like a tank. It was the best washer ever built, besides maybe a Speed Queen. But those two were the two best washers. I mean, you couldn't go wrong. Then Whirlpool came out with something called a direct drive washer. And they still had a transmission in it. And also with the transmission, they also had a braking mechanism, like a car brake. We'll talk about those machines in the future, but the older one that I'm talking about in the 80s, they haven't made that since late 80s, 90s, when the direct drive washer was introduced and replaced it. And one of the things is it was less heavy mechanical stuff. So you also have to think about, it's not always the design of the machine, that it is also, when you have something super heavy and you have to ship it, it costs money. So if you got a washing machine with a huge transmission in it or whatever, it costs more money to ship than if you had an empty box the same size because of the weight. Panasonic came out with a microwave, but our microwaves, you know, we've seen the videos or whatever, transmission, cap, diode, magnetron, and everything else. Panasonic came out with something called an inverter board. It was just a circuit board that took the place of the transformer, the capacitor, and the diode. If you ever picked up a microwave, they're sort of heavy, and one of the heaviest parts is the transformer inside that microwave. Mm-hmm. The inverter board on the Panasonic, you picked it up and it was like, wow, it's missing something. Mm-hmm. Well, they put it onto a circuit board, that big transformer. Now, they had a lot of issues with that inverter board that's still being used today by some manufacturers, but to ship it from Japan to America, it was a lot lighter, so it cost less. So the direct drive washer was more of an evolution for that. When I went to school, they had a washer called the Design 2000 washer, and this is in 1983. And it was the first direct drive washer that I've ever seen. And it was there in the class, but nobody really even worked on it because it was just a prototype. No one knew anything about it. But what happened is manufacturers usually design these machines and they put them in test markets. They have certain areas and neighborhoods that people allow them, think, oh yeah, I'll take a new washer, but Whirlpool or GE or whatever manufacturer will go to the customers' homes periodically as part of the deal, giving them new machines. So they go in there and check everything out to see if the machine started having issues, because they cannot duplicate real world situations in a factory or in a test lab. It has to be real use by a customer. And you know, like the direct drive washer, when it first came out, it'd be full of water, and when it went to spin, it went right into spin, but it spinned with a full tub of water. Mm-hmm. Now on top of the washer, they have a tub ring, and that usually was okay, but then it started happening that the washer was spilling over. It's like when you put too much sugar in your coffee and you spin it too fast, the coffee goes over the side of the cup. Mm-hmm. So Whirlpool had to redesign the transmission on that direct drive washer to what we call a neutral drain. So the motor went one way for wash, went the other way to drain, and when it did that, the transmission went into a neutral gear, just like car neutral. So the motor's running, but the transmission's not turning. Then the motor would stop and restart, and the gear would engage in that transmission. So one of the biggest problems we had then, I know we're talking about VMW, but I'm talking about something else. One of the biggest problems we had then was that we had the one washer that had the regular transmission on it, but then we had these new washers coming out with a neutral drain. Now some people were saying, oh, this washer needs a transmission, and they put the new transmission in the older design washer. Well, the timer has a built-in pause where it stopped and restarted. Well, if they put the wrong transmission in the wrong machine, it never paused and restarted, so it never went into spin. So that's different from today, but that's the evolution. And then they came out with these newer washers, and one of the reasons why I came out the newer washers was for the government, who said, hey, we need to use less electricity, we need to use less water and everything else. So these machines came out with this design. Now Whirlpool's had this design since the early 80s in something called the World Washer. And the plastic gears and stuff in there was called a splutch. It was a plastic clutch, and I don't know how they came up with the term splutch, but that's the gearing mechanism. We're going to take this one apart, we're going to break it down, we're going to go through those pieces, talk about what to look for problems, how they work, and everything else. So we're going to go over the diagram just a little bit. We're going to go over diagnostics, we're going to go over tear down, we're going to talk about components of this machine, and if you guys got any questions, just don't hesitate to ask, okay? So in this washer, we have a diagnostic cycle. We'll go into that cycle after we do the breakdown of the components and how they work. And then we'll talk about how to use the troubleshooting for checking the unit out. Here's the diagram, and I think I have it on this program right here. Here's the diagram. Very simple. I know for some of you, you're looking at, say, you call that simple because you're just looking at lines, you don't know what they mean. Yeah, I get it. But ACU is the main control board. That is the brain of this washing machine. Where's the control we took off of this washer? ACU, automatic control unit or something. I think that's what they call it. But this is the ACU, the main board. This takes the place of a mechanical timer like the older washers. This is the brain. First of all, the cycles in a washing machine, and you know, I never really explained what the cycles are, but the cycles are when you go into normal wash or permanent press or delegate and you press start, a timer would rotate. It would fill up, it would wash for 10 minutes, and then it would turn and then tell it to drain, and it'll turn and tell it to spin, and the whole 9 yards. You can't do that with this machine. You press start, and there's an electronic program. Step 1, fill water. Wait for the water to fill. Did it fill? Yes. Step 2, agitate. How long does it agitate? Depending on the cycle that a customer selected, heavy, whites, whatever, how much time did it agitate? Then the board say, well, are we agitating the motor on high speed? Are we agitating the motor on low speed? What's going on? So the control unit has a logical step that it goes through, step by step by step. We call it a program. Just the same thing like your computer. You do something on a computer, and the computer says it can't do it, it's because the program asks questions as it goes through. Does it do this? Yes or no? If it's no, then go over here. If it's yes, go over there. And that's how this programming thing works. There's relays built into here, and those relays send power out, but they are not mechanical relays. Looking at that diagram, can someone find me one of these relays that are on this board in that schematic? It's inside this box right here. Well, let's take a step back. What parts make up a relay? What do we need to make a relay? A coil?
A switch.
And a switch. So a relay is a coil, looks like a water valve, but then you have a switch here, and is that an open or closed switch? Open. So sometimes you'll see it or sometimes you won't. You'll see a dotted line. So when power is provided to the coil, it becomes a magnet and closes a switch. Do you see any of them in this rectangular box here?
Can't see.
You can't see the board, or you can't see any on the board?
I can't see the objects on the board.
So if you want to come closer, you guys can come sit a little bit closer.
Is there one on the border? I can't see that.
Are you talking about there?
I can't see that.
That says run capacitor. Oops. Let's undo that. And here.
No.
That's a run
Yeah,
capacitor.
and now you can see the
It looks like a coil.
Right. Actually,
Hey.
feel good now.
right? But now check it out. Is it? Well, I have a guess, but I want someone else to guess first.
I know you know the answer. Anybody else know? What is it that is controlling the components from the board that's telling the water to come in, telling the motor to run, telling the drain pump to drain?
The timer?
There is no timer, it's a computer board. So we don't have a mechanical timer. We talked about the timer yesterday. We don't have switches like that. We have the board that has switches built into it that are sending power to these components. They're all right here. Those are your relays, but they're not the typical relay that I drew for you on the screen a minute ago. A relay, again, is like this. Switch could be open or closed. This is a switch and a coil. The bottom part being the coil, which is magnetic. When given power, it closes a switch. And the switch is on the top of the machine. Okay? But that's not what's on the board. What's on the board, if we look at it, it's a triangle with another triangle. Oops, can't draw. With another triangle, two lines like this, this, and then we got a little flag coming off of it. Let's go back to the diagram for a second, and let's zoom in on that just for a second. Do you see the two triangles and the little flag that I have coming off of there?
Diode?
Well, yes, you're right about a diode, but it's not just a diode, okay?
Triac.
It's a triac. Very good. What's a triac?
Isn't that like a concept?
It's what?
The digital switch.
It's electronic relay. This is called This is called SCR or triac. Silicon controlled rectifier. Rectifier is a diode. It's another name for it. But it's called SCR, silicon controlled rectifier. That's what a triac is. Now back in the 80s, microwaves had triacs in them. I think in one of these boxes and parts here, I'll find after the lecture and show you what an actual triac itself looks like. And there's a specific way to test it, but we can't test these triacs like we checked that one, because the triac in a microwave was just an external part that sat inside the microwave. Now we're talking about the big brown microwaves that came out in the 80s. Okay, the 70s and the 80s, the first microwaves that came out. They had a triac in them where the control board told the triac to send power to the transformer instead of having a relay on the board. Okay? So you said you said that it was a diode, and a diode is a symbol just like that. It's just a triangle against a wall. And what that is it takes AC voltage and converts it to DC, because it only lets electricity flow through one way, and then the other way is blocked. Okay? So it doesn't allow electricity to flow through it, and it converts AC to DC. It just blocks power from going one direction. But if we look closer at this SCR, which way am I blocking power?
Both ways.
What'd you say?
Both.
Both directions. I'm blocking power one way and blocking power the other way. So I got two diodes facing each other, and they're both blocking power from going to the left and blocking power from the right. So what good is that? Because if it's blocking power both ways, well, I can see one way, at least I make it DC, like in a microwave, we have to convert AC to DC to pulse the voltage to the magnetron. But on this, the diode is to completely shut it off. No power goes through. But that's what this little flag here, and if you go back to this diagram here, the little flags that are on top of these are a gate. It's a low voltage signal that is applied to it, that when the low voltage signal from the actual control board comes here, I don't remember which terminal it was. We used our meter and the batteries in our meter to energize the gate, and then when you took it off one terminal, it continued to give a reading. If the triac was bad, you took it off and then it would not give you a reading anymore. So when low voltage from the control board is applied here, the relay closes. So why don't we just make a mechanical relay? Why this electronic relay? Well, one of the reasons why we use an electronic relay is that motor right there. These relays can handle switching much better than a regular relay, okay? A relay has to have physical movement. You have a magnetic coil that's closing a physical switch. And when power's off, a spring opens that switch. And then we turn the magnet on and it closes the switch. And that's fine. But one of the important things about switches is when they open and close, they need to smack close. They can't go like this. Like you would want a switch to close quietly and softly, right? That's no good. Because when you close a switch slowly or open a switch slowly, when the switch is closed, it's drawing electrical current. And that electrical current, when you open and close slowly, it's not making good contact until the very last second. And that causes arcing. And then you got two metal points on there when it opens and closes. But that arcing also is almost like electrical welding. So it takes the surface of the switch contacts and burns them. If you look at old switches like contactors on ACs and stuff, they have switches and eventually you see those points start to burn. And what's happening is those switches are drawing so much electrical current, you're burning the points out on the relays. So with the electronic relay, well, why did we do it for this motor? Well, we have no transmission in this washer. And a transmission, you know what, let me see if I can just bring this up for a second. Oh wait, I already have tab open, hold on a second. Oh, it didn't open, that was when I was opening. Okay, hold on. Okay, these are not transmissions, okay? You're gonna see them on some of these machines, like the one we're gonna take a look at. That's not a transmission. A transmission has gears like a car, okay? That is a transmission. That has gears inside of it. The motor's directly connected to that, and it has a plastic coupling in between. That was the direct drive of the Design 2000 that I told you about. You probably won't even see the belt-driven transmission on here because they stopped making them before the internet. See if I can find, let's just find that one.
Belt-driven transmission?
Yeah. Hold on a second.
Wait, so were there two belts?
No, hold on a second.
No, wait, no, the motor would be.
Okay, so no, this is it right here. That is the transmission. That's like a motorcycle transmission or something. You see how big that thing is? You guys probably go through a package and when you first come to class and it says check a wig wag. That's a wigwag right there. Spin and agitate solenoid. Oops. Let me go back. I didn't mean to do that. That right there is the, man, it's been so long since I did that. That's the spin and that's the agitate. When you energize that solenoid, it shifts a cam and that goes gears. But what happens is a pulley's always turning in one direction by the motor. And through the gearing in here, just like a train, it causes agitation motion, backwards and forwards motion. It's done like this. You have a pinion gear, and it went to a drive gear. So the drive gear, let's see, there's teeth here. The drive gear was a completely round gear like this with teeth on it. And it was held in by the center shaft. So this is where the belt was. The belt's turning this, so it's turning one direction, and then this big wheel's turning. Now, over here is the main shaft that your agitator's on. And we want this to go backwards and forwards. But if this is only turning one direction, and this is only turning one direction, how do I get this one to go backwards and forwards? Well, we put a hole over here, and we put something called a connecting rod. Now, as I rotate it, this piece is going around, so this is going to go backwards and then forwards and forwards as it rotates around in the circle. So now I'm creating a back and forth motion, right? And then on here, we have another gear that's like this, and it's called a sector gear with teeth on it this way. And those teeth would go to this piece here. So if I go backwards and forwards with this shaft as I'm going this way, like a train. You know how like a train, like that piston goes backwards and forwards and moves that train? It's the same principle in this transmission. It's going backwards and forwards, and this gear is going backwards and forwards. It would be rotated this way, but in my drawing I have to do it that way. The agitator would go back and forth. That's how we create washing. Fine. And when we go into spin, we just disengage that gear and we go into spin. That has nothing to do with the spin. Now going back to the picture real quick. That's your brake mechanism right there. Dang it, I didn't want to do that. That's your brake mechanism right there, and that's your clutch on top. Clutch like a car. You can't just shift into one gear or the other while the engine's running. You'll break the gears of the transmission. So you have to have something like on a clutch that causes a slippage motion. That's where you got the splutch, the clutch and the transmission piece together, okay? We're talking about the other one. So here you can see the spinning and the shaft. Oh, there's a great picture. Let's see if I can get this picture right here. Here is the drive pulley going to a pinion gear to here, going to the drive gear to a connecting rod. That's our sector gear, right? Let's see if it shows a bigger picture here. They might show it going backwards and forwards, just like a train. Okay? That's how agitation was done back in the 80s. That transmission was a beast. Even though we had one customer that kept breaking those gears. Those gears are this thick metal. She was filling it up with so much clothes, and she was using a 2x4 to shove, like, and she put so much clothes in there and bound up the agitator couldn't work, and it damaged the gears. And we would rebuild these transmissions. When we took them back from a customer's house, we changed them, took them back to the shop. Some days when workload was light, one of the technicians, I've had to do it once or twice, go into the shop, we'd have 20 transmissions, take them apart, drain the oil, rebuild the gears, put new gaskets, and put it back together again. That's how that transmission works. Wow, I was surprised at someone. That's actually not even the regular connecting rod. I've never seen it that, because the connecting rod was a solid piece. I used to have that transmission here. Remember, I started teaching in the 80s. So, guy came to me, the instructions to change the belt on that. He says, man, he says, I don't care if I learn anything in your class. I want to know how to change that belt. I spent 3 hours and still didn't finish it. I said, okay, it's the last thing I'm going to teach you before you graduate. And the guy got all upset. What do you mean it's the last thing I teach you? Because I'm going to show you how to do the whole washer in 15 minutes and change the belt. I don't follow the instructions on the package of the belt. I do it my way. But if I show you how to do it, that's the only thing you wanted to learn, you won't come back tomorrow. So that transmission was replaced, okay? So let's get back to this. So we understand how that agitation works. And you're like, well, why are you going off on this other washer when you're talking about this VMW washer? Because this don't have a transmission, it don't have a sector gear, it agitates back and forth like the other washer, so how do we get that agitator to go back and forth? Well, I used to think this, but it wasn't correct, is that the motor would run one way and stop, then the motor would run the other way and stop. Then the motor would run one way and stop, and then go back the other way. And they used the motor going backwards and forwards. Now this all ties into the silicon control rectifier. Every time I want the motor to go one direction, those of you who learned reversible motors, you had to send power through a winding in the motor to make it go one direction. But when you wanted the motor to go the other direction, you had to send power the other way. So you'd have to have two relays. You'd have to have one relay to make it go clockwise and turn that relay off, and then turn the other relay on to make it go counterclockwise. Well, if it goes woo, 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 as far as like how fast it switches back and forth, that mechanical relay ain't gonna last. It's gonna burn out. So we're gonna use these electronic relays. That comes to the schematic of why and how they did that on this motor. I know it's a long way to get there, but let's just talk about this. Now, if we look here, this is line 1 coming in. It says L2, but it's really neutral. Power comes in here, goes through here, goes to the motor, and then depending on which one of these relays is going to determine the direction of our motor. For sake, I'm just going to say CW and CCW. So in other words, if I turn this one on, the motor goes clockwise. If I do the other one, it goes counterclockwise. So when we send power from here, we come in here, this power goes through the motor and goes out this one, but it comes through this capacitor for the other way. Okay, not for the other way, but for the other winding. There's two windings in that motor. Now, in most motors, we have a start winding and a run winding. This motor has two windings that are identical to each other. It's just the way we put power to the motor to determine the direction of our motor. So if we put power here and I send this way, let's say it goes clockwise. Now I want to reverse the direction. So I'm going to take the power off of this one here, and I'm going to close the bottom one. So now I go straight through this one, but I go through the capacitor on the other one. The one going through the capacitor is what winding in the motor?
Isn't this a run winding?
It is the start winding. The start winding gets power from the capacitor because the voltage builds up, it kicks the start winding, help
so
get
they're
the
going to
motor
use
going.
start winding in the agitate?
We're going to use the start winding and run winding to make the motor go one way or the other. This one is going to be the one that gets power all the time. This one's just going to get power off the capacitor to start the motor.
Okay.
If we look at our direct drive washer just for a second, let me go here and I'm trying to figure out which one is the direct drive in the book. Hold on one second. When we look at this wiring diagram here, let's look at this diagram here for a second. No, they don't show it, but the direct drive washer is down here, I'll show you. Right here. There we go. So we got our two speeds. Our start winding is in series with the capacitor. Very similar setup as to the other washer motor. Okay? And then we reverse the direction by sending power this way or that way through the start winding. That determines the direction of the motor. But this washer is the direct drive, and it had that transmission. I showed you that they were connected together. We'll talk about that washer another day. All right, let's go back to the diagram. So what happened, oh, no, sorry. So what's happening here is these two are coming on and off and on and off. Just going on, off, on, off, on, off, depending on which way we want the washer to go. We use the motor now to create that back and forth washing action. Does that make sense? So if we're testing the motor for continuity or resistance or whatever, we have 3 wires, we have 2 windings that give you the same exact resistance. If we look here, what colors are they? Colors aren't there. They're not giving you any of the colors of the wires. But we can check it from the computer board. Now, we're not gonna do it right this second. We're gonna test these out. I just realized now I'm probably gonna have to break this lecture up into more than one day so I can go over everything properly. But we'll go over ohming all these out after we go over how the function and everything works. So that's the motor going back and forth. But what do we want to go back and forth inside of a washing machine? The agitator. What other part inside this tub here goes back and forth? Can you get this, Ms. Z, the inside of this? Huh? The spinning basket. So we have the agitator in here which goes back and forth, but then we have this stainless steel basket that spins. Can we have both of them move at the same time? When they spin, yes. When I spin, if you notice, the agitator rotates with the tub. And that's important. Why? Thank you.
Isn't that the thing about the reverse threading and it keeps it in place or something like that?
No. That's the nut that's on your left-hand thread. But if the agitator was stationary and the basket's rotating around it with your clothes, what's going to happen? Clothes are going to wrap around the agitator and get bound up on the agitator. And the other problem we have is that when it's agitating, we don't want the basket to be spinning because it will also wrap the clothes around the agitator. A lot of times you go to someone's house and if they tell you, hey, my clothes are all wrapped around the agitator, most likely the washer is agitating and spinning at the same time. It could be in the agitate cycle or in the spin cycle, but it's agitating and spinning at the same time. Try to do that. You know, it's like. So if you see it clothes wrapped around the agitator, it's usually because it's doing both at the same time, and that's not good. Okay? Now the next component that we need to work with this is our shifter. The shifter is a mechanism that engages the machine for spin and for agitate. That's located down here, okay? So let me open this up for a second here on this washer. So here's our motor. When we want to spin, the motor just goes one direction. Can you hear that noise? That's the basket spinning. What's that noise? Water. Well, wouldn't it leak down the floor if I laid it down? So I'm going to turn it around. And I'm going to rotate it. Where's the water? Is there water in there?
It's in between the basket and the.
It's in this plastic ring right here. This plastic ring is a balancing ring. That when you are spinning, one of the biggest problems about washing and clothes is balancing. It's very important that a customer loads a machine somewhat properly, but it doesn't matter how well they load it, when we wash, what's going to happen to those clothes? They're going to move around. And when we wash clothes, one of the things you got to tell customers is that they need to load properly. And you're like, yeah, but I can't tell them like to put this here and put this here. That's not what I mean when I say load properly. That if we're washing jeans, we wash jeans. We don't really want to wash them with socks and underwear and t-shirts. Why? Towels, when they're wet, towels or jeans are a lot more heavier than a t-shirt or socks and underwear. So if you have 5 pairs of jeans, 3 pairs of underwear, and a couple t-shirts in there, if 3 or 4 of those pairs of jeans, as you're washing it, caught to one side of the basket, when it goes to spin, it's like having a new tire put on your car, but they didn't put the weight on it to balance it out. The machine's gonna vibrate and shake. So what this ring does is that if you got a lot of clothes on one side of your basket, the water in the ring goes to the direct opposite side through inertia and actually acts as a counterbalance weight. Doesn't always work too well. And especially on these machines, let me just get this piece here. On these machines, this whole tub is hanging here by these rods with these shocks on them. Okay? This manufacturer, Whirlpool, has partnered with Samsung. So when you look at a Samsung machine, you'll find out that there's a lot of things they have in common between the two. They do have slight differences because they are different manufacturers, but one manufacturer has worked with another manufacturer to create a design. GE has worked a lot with LG and their laundry products and refrigeration products. You'll find that manufacturers work together. I remember back in the day when I was working for my company before I had technicians, there's a property up by the Fort Lauderdale airport that had a lot of laundry centers, you know, the washer and dryer. It said GE, but it was a Whirlpool washer dryer. It's like the little white one laundry center that we have here, but it said GE. So you'll find machines that are designed by one manufacturer sold under another manufacturer's name sometime. But getting back to the point of this, these springs here, at one point these springs would lose their tension. And when the machine goes to spin, they don't support it as well. It's like having bad shocks on your car. And this whole tub will bang and shake even if the load is perfectly balanced inside. And we have to change. If you go and talk to people, they've changed these shocks numerous times. The problem is it isn't one set of shocks for all. You know, you have to order by model number. Some are longer, some are a little bit more heavier duty than others, but make sure you get the right shock for the right machine. So we have this counterbalance weight. This agitator here is a single agitator. Whirlpool direct drive washer has what they call a dual action agitator, where the bottom of the agitator goes backwards and forwards, but the center of the agitator only goes one direction. When the agitator goes backwards, that piece doesn't move. When it goes this way, the center piece goes like this, then it does this, and like this, and like this. So what happens, the center piece acts like a corkscrew and pushes the clothes down to the bottom of the tub, while the bottom one's going backwards and forward doing the scrubbing, washing action, and the clothes on the outside are going back up. So we create two dual action going on. We have one action of the clothes on the side going up and being pushed down in the middle, and then on the bottom they're going backwards and forwards for the washing action. Now this one doesn't have that dual mode. It has the corkscrew to push the clothes down, and it has the agitation back and forth. But if this is going one way like this to push it down, and then it goes back the other way, is it really doing a great job? I don't really think so, but that's how they designed this machine. All right? So we said the shifter. Turn this thing around here. So the shifter is this little piece right here. It's got a motor on it, and it's got a little shifting piece here. This is our splutch or clutch assembly. And this shifter is what enables the machine to agitate or to spin. And we'll talk about the pieces of the shifter because they're not showing you what's going on inside the shifter, that there's a lot more to it than that. So by taking this off, let me just go ahead and take this one nut off. When you go to take this off, I loosened all these bolts prior to the lecture. What you want to do is hold the belt, squeeze the belt tight, and the belt wrapped around your pulley will keep your pulley from turning when you're trying to use the socket to remove the bolt. So you just take like this, and then just use the pressure of that belt to hold it in place. Now, it was a lot easier than said. Now, you can slide this right off with the belt. If you want me to take the belt off first, which you can still pull the belt off. You could take the belt like this and hold the belt like this with your hand while you're trying to break the nut free. Use the belt like an oil filter wrench to hold this so you can take it apart. Okay? So this is your drive pulley like that other transmission. It's just driven by the belt. But this pulley has teeth on the bottom of it. You guys see the teeth? These teeth engage with these teeth. All right? So I'm going to go and take the shifter off first and show you how the mechanical part of it's working. Did you guys give me a Phillips screwdriver? Is there a Phillips over there? That's not Phillips.
Okay.
Okay, I need a Phillips screwdriver.
Excuses.
Excuses.
Your glasses? So you can't see your glasses?
Well, that's what makes it work.
No glasses on the scene, huh? So you need glasses?
Yeah.
You is smart.
So I'm going to go ahead and remove this shifter here. Should have two Phillips screws, one here and one down here. So now I'm just going to take the shifter out. Now what does the shifter do? The shifter slides this piece here. Now watch what happens to this when I move the shifter backwards and forwards. It goes up and down, right? So what happens is when it's down, where did I put that drive pulley? There it is. When it's down, it doesn't engage with the teeth on this pulley. Okay? When it's up like that, it engages here. So what does that do? On washing machines, the shaft of the transmission is two parts. Okay? Let's go back to that picture of the washing machine transmission. Let's go back to, let's see if I get a good picture so I can show you guys. Yeah, I'm not really seeing a good picture of it. So this is just the agitator shaft. So basically, we'll have to take this apart and look at it, and I'll break it down for the next video. So what happens is there's a center shaft and there's an outer shaft around it. Between those two shafts, there's a seal right here so water doesn't leak down. But where the outer shaft is, there's another seal which is at the bottom of the tub right here that seals the outer shaft. So we have two sets of seals. We have an upper seal and a lower seal. The upper seal is inside the transmission. The other seal is outside the transmission where the tub is to keep the water from leaking out. We'll break that down when I pull this out. Probably gonna have to do that in tomorrow's lecture. Okay, so that's this piece. So why is that important? Well, I'm gonna go ahead and take this piece off here. Just squeeze it in and rotate it. You can. Rotate it. I'm going to take these pieces off for a second. I'll go over these in a minute. Now if we look, we have two shafts here. The one shaft is the center one here. And if I put the pulley on it like that, I'm just turning the center one. I know you can't really see it, but if you look at this gear on the outside, the gear on the outside is not turning. Only this shaft is turning. But when this is on here, it has splines on the inside and splines up here. The splines on the inside are grabbing onto this shaft right here. Now watch what happens when I turn this. But if I hold the outer shaft while I'm turning the inner shaft, watch this. What's happening here?
Isn't it still spinning?
What?
It's still spinning, right?
It's spinning, but what's not happening?
Uh,
See, before this was happening. What's happening here that's not happening now?
Yeah, I was gonna say, look at that.
I want to spin it together. With the inside
The agitator's not moving on one of them.
No, I was looking for that.
Yeah.
Watch now. I'm gonna spin the whole. I'm spinning this. What's happening here?
It's agitated.
The agitator's moving.
Yeah,
The
yeah.
basket's not. When I
Yeah.
do this, they're both moving. But if I hold it,
okay.
but if I hold this one still,
Did you see that, Josh?
is the agitator rotating?
My contacts.
But is the agitator rotating right now?
Yes.
It is? Oh, maybe I'm not holding it. Wait a minute. The basket's rotating. The agitator's moving also?
Well, it's holding still technically.
The agitator's not staying still?
The agitator moves with the basket, but it's not itself rotating. It just moves with the basket.
Okay.
It's slower.
It's separating the agitator from the basket. So when we agitate, the agitator can move separate from the basket. That's
Yeah.
what that is.
Yeah.
So what happens here, on this piece here, there's a little spring inside of here like this, that is pushing it upward. And when the shifter shifts these two like that, both shafts turn and the machine spins. When the shifter goes the opposite direction, this piece goes away and separates, so the pulley here turns and only the agitator moves. This is how we're shifting from spin to agitate inside the washing machine. And that's all done with this shifter right here. This little piece right here. Now these two pieces, they are what raise and lower that cam. And when I rotate it, look how it goes up towards you guys. And when I go the other way, what's happening? It's going down. So when the shifter moves it one way or the other way, that's moving this piece up and down for engaging into spin or agitate. Okay? Now let's take a look at something. It's not shown on this diagram, but there's logic built into this shifter. Some of the older washer diagrams have that logic. You see these two little plastic pieces right here? Where my finger is? They go inside this hole. Like right where my finger is, and I'll turn it around so you can see. There's a little piece of plastic made black here. And then when I rotate it, it spins around with this shaft. And this piece here sits over that plastic. So in other words, the plastic is here and those two fit right over that plastic. And as the plastic rotates it, this is like a hall sensor. This is telling the machine whether the basket is spinning or not. Because we do not want the shifter to try to shift into agitation or to spin while the basket's rotating. It'd be like trying to go from drive to reverse, you know, while the car's rolling forward. What would happen to your transmission? You damage your transmission. Well, these are all plastic gears that have to engage together like this. And you hear that noise? You hear that on a washing machine, and something might have went wrong with the shifter, but then these teeth will get ground up. And you have to replace this clutch assembly with the pulley. Okay? So the shifter is what engages and disengages this for spin and agitate. Alright? The hall sensor here is what tells the machine, hey, it's still rotating. Like we were in a spin cycle. I stopped sending power to the motor, but the inertia keeps causing it to spin. Why? Because this one, unlike the other washers, don't have a braking mechanism. It has no way to know that the motor's supposed to stop spinning the tub. The motor's not getting power, the motor's not running, the tub is just spinning because it was going so fast, there's so much weight to close, it's gotta slowly slow down. Okay? So this is a safety to say, hey, don't shift yet, the machine's still spinning, we'll wait for it to stop. But that also has to do with the locking mechanism of the washer. Some washers have a lid switch. That's it, just a switch. You raise it up, The machine stops spinning because it has a mechanical brake mechanism. Some washing machines have a lid lock. This unit, it's a lid lock. So let me just bring my camera up for a second here. And the lid lock is, where did I put that thing? Right here. So this is the lid locking mechanism. The lid locking mechanism will lock the door shut and keep the customer from being able to open the lid until the machine has completely stopped rotating during the spin cycle. Because if it's spinning and they open it up and try to reach for something or stick something in, it could wrap around the agitator. And like I said in previous videos or whatever before, back in the 80s, they said you'd never bypass a lid switch, because if the customer opens it and it's spinning with the lid open, one customer went to throw a towel in there and it wrapped around the agitator and just practically ripped their arm off their body.
Wait, that's what happened?
I don't think it ripped their arm off, but definitely messed up their shoulder and just about ripped the arm off.
Brutal.
So we have to have, that's why these front load washing machines and these other machines have these locking mechanisms, because they do not want the door to be opened, because the machine has no way to physically stop the rotation of the tub. It has to slow down and stop rotating on its own. Now if it has a locking mechanism, that's the way it would work. If it's just a regular lid switch, like the old direct drive washers, you lift it up and you see it spinning and all of a sudden, and it stops, almost like slamming on the brakes. And that's what's happening. The brake mechanism's being slammed on there to stop the unit from running. Now, I'll show you this switch mechanism in a different diagram. But this here, not only does it have this sensor here sensing the rotation, and we have this shifter here which is engaging and disengaging the pulleys for agitation and spin, there's a little tiny switch in there. And that's how the machine knows whether this has successfully went from agitate to spin or spin back to agitate. Because we use this to stop the motor, the shifter, from moving while the motor's running. But we don't want the motor to turn on until the shifter completely shifted in or out of gear. So there's a little tiny switch inside of there that is activated, just opens or closes. And the board sees that and it knows, hey, the shifter's in the right position now, we can start spinning, or it's in the right position, we can start agitating. And that's all done through the little micro switch that's built into the switch mechanism here. So we can engage and spin and disengage spin here. Here we have a standard capacitor. I'm not going to go too deep into it, but I showed you the capacitor on the diagram for the motor. That's this piece right here. That capacitor can be tested out with a regular meter that has a capacitance tester, or an ohms, if you know how to do an ohms test on a capacitor. Maytag, who has now been acquired by Whirlpool, has these washing machines, and apparently some of these capacitors are shorting out. And short means, like when you tested 0 ohms, a closed switch is a short. A piece of wire is a short. There's nothing stopping the voltage. But when that shorts out, it causes all kinds of havoc. It burns out the boards. The one I have here with the black lid on it, the Maytag one, had a bad board when I got it. I changed the capacitor in the board, the machine's working just fine. But it is something to know that these newer Maytag ones have had problems with the capacitors, which has caused other problems with the machine. All right? So the shifter has 3 parts: the motor, the sensor, and a little micro switch. We don't replace just a piece of that, we replace it as a whole complete assembly. But you need to know how the assembly functions and works for troubleshooting, which we'll get into troubleshooting as we get into it. So I'm trying to cover all these pieces as we go. Any questions on this stuff so far? All right, so We only have two other parts down here that are functioning parts. One is the drain pump. Drain pump only drains, doesn't recirculate water. Some washing machines, the pump can recirculate water up to the tub and back down. Some just drain out. That's all this does is drain. The pump has nothing to do with water coming in. That's the water valve. The drain pump is to throw the water out. Okay? So we got capacitor, drain pump, drive motor. And when we check this drive motor, if we look, we have 4 wires on it. 1, 2, 3, 4. One of them is just ground. This is ground. All right? So if we test it and we go from this wire to this wire, we're gonna have, let's just say 8 ohms. We go from this one to this one, we have 8 ohms. But what if I test this one to this one? 16. That's it. That's how you test this motor. We're gonna take a meter now, we're gonna go ahead and test this motor. Someone wanna come help me here and do the test? Let's go ahead and take this motor out and we'll do it on the bench. Look how strong I am. I'll take these bolts out by hand. What do you guys call it, Superman?
You can test it inside the machine, couldn't you?
Yes, but we can't see the plug because it's facing down. And we can check this motor from the control board, but when we get further on, we'll talk about that. All right, first of all, we look at this plug, and I'm gonna hold it here so that, can you guys see it good on the camera here?
Yes.
Okay, so I'm gonna show you here that we have 4 wires. But if we look at this one wire here, it's attached right to the motor on the ground. Okay, so this one here is ground. We're not even gonna bother to test for that. Now we got 3 wires here, and I don't know which one's which. So we got the 3 terminals to your right, right to left. So we're gonna check the first 2, first and third, and then the second and third, okay? So let's go ahead and, can the camera see that?
Yes.
Okay, so check the first and second one there. And what's our reading? Are we on ohms?
Yeah.
What's the reading?
12.4.
Okay, now check first and third.
6.3.
Okay, stop for a second. Okay, so the first and second was 12, and the first and third was 6.3. What do you think the second and third is going to read? 6.3, right? So go ahead and check the second and the third one.
Yeah. 6.2.
6.2, which is close enough. So like I said, you'll have 2 windings in there of exact resistance, and the third one's just gonna be them 2 added up. I was close, I said 8 and 8 and 16, but really it's 6 and 6 and 12, right? Or 13. So that's it, that's how you test this motor. If these 3 windings are good and this motor don't work, it's either the control board or the capacitor. But what one thing would you do before we just say those are defective? Check to make sure that the board is sending power here and here, here and here. See if the power's coming out of the board telling that motor to run. We check it right from the control board up top. Right? Any questions on what we went on so far? Because
You
we've
can
covered.
basically check everything from the board, couldn't you?
Yes and no. Sometimes some things can't be checked on the board. A lot of things can be, depending on the manufacturer. The other day, we had a GE front load washer, and we had certain things that we could test on the board, but we also talked about certain things you can't check from the board. Sometimes this will go to the motor, but the other side of the motor just goes right back to the plug. It doesn't go through the board, so now you don't have 2 wires on the board going down to the motor. It depends on the design of the machine. Okay, I'm gonna stop right here. We went about an hour. So tomorrow, I'm gonna leave this all like this, and we're going to carry this lecture tomorrow, and we'll do about another hour tomorrow. If it takes me 3 hours, 4 hours, I'm gonna go it, but we're gonna go over everything. We're gonna pull this transmission out. We're gonna talk about servicing it. We're gonna talk about troubleshooting it. We're gonna talk about testing from the board. But I'm not gonna talk for 4 hours, because you guys, you know, I'm already losing a few people here who's sleeping, so. Any questions about what we discussed though? The shifter, the motor, the triacs, the parts of the board? Any questions about that? No? Okay, so we just did this part of the diagram. Look what's down here. I will talk about this because this is one other part of the machine. Let's move this washer out of my way. Alright, so I was going to stop, but I do want to go over one more thing. Oops. There is the shifter motor. This is also part of the shifter. Look how the shifter motor is on a plug on the board. Are these components of the shifter on the same plug on the board? No. That these are on plug J12, where this one is on plug J2. So the shifter motor, which is this motor, is getting the power from one plug on the board, but these other components getting power from another. Most likely because the shifter is running off of, well, let me zoom out a little bit. There we go. Can't touch it too, but zoom out just for a second here. And as you can see, line one's coming in and sending power to my shifter motor. So the shifter motor gets how much power? 120. If it's line one or neutral, goes to a part on the machine that has a computer board, you know that part in the machine is getting 120 volts. Okay? If that part, both wires of that part, both go directly back to the board, you can't just assume it's 120. Now on this motor, they do specify that it is 120 volts. I'll first show it here on the camera, 120 volts. But if you guys look over here, you can see right above my finger it says 120 volts. See where my finger is? See that there where my finger is? It tells you. So if it says 120 volts on there, could you take a test cord and put power to that motor? Yeah. If you wanted, you didn't think the shifter was working, but you wanted to see if the shifter was working, we could put 120 volts right to it. Okay? But these other components, are they 120 volts? Are these components going to line one or neutral? No. But what also do you see here? Minus 5 volts. So this is running off of low voltage. Everything else, the sensor and the little switch inside. Remember I told you there's a little switch in there that's shifting when it opens and closes? There it is there. I didn't even look at this diagram before I started lecturing. I would have known it was there. But that's the switch that tells the board. If that switch is closed, it's in agitation. If that switch is open, it's in spin, or vice versa. On the other diagram, it does tell you which is which. I think open, spin, and close is agitation. I don't remember. But that's how the board knows the position of the shifter. But the optical sensor is here. What does that say on the top? For those of you people can't see. What does that say on that line? Tac power. What is that, like Ninja Turtles? Tac power? What is tac power? Tac is short for what? What's a longer word that starts with tac?
That tac thing.
What's in
The
your car?
triac thing.
No, what's in your car that has a tac something? You got two gauges in your car. One tells you how fast the car is driving. What's the other one over here?
Battery.
Yeah.
Your tachometer shows you the RPMs of the car, how fast the car's
That's what
rotating.
that's called? You knew what that was called?
But in a stick shift car, like my stick shift car, when you're driving, that tachometer's to the right of your gauge. That tachometer is telling you how fast the engine's going. And you can only spin the engine so fast before you start spinning bearings and damaging the car. So you get to something called red line. If you hit past the red line, you can burn out the motor. But when you're driving and you got a stick shift car, the tachometer, you see it go up, you have to shift to the next gear and it'll drop down, and as you speed up and then you shift and it does that. The tachometer is telling you speed. So this optical sensor is doing two things. One was to tell if the board is running and rotating, but the other thing the tachometer does is let the washer know how fast it's going. Whether it's going high speed, low speed, or whatever, it's a tachometer.
Optical
On some of these washers, we call them a hall sensor, but it's basically the same principle. A little piece of magnet spinning around, and every time it goes past the sensor, it pulses the sensor. Or they use an infrared light, they have holes in it, and every time the hole passes, the light passes through and pulses on and off to the optical sensor. Now this works like an optical sensor. This isn't like a hall sensor, it's an optical sensor. It's the same thing like when you go into a clothing store and it has that little infrared light that goes to a receiver on the other end, and when you walk by and you block that light passing from one end to the other, a little bell rings letting the people know you're in the store. And that's how the optical sensor works. If you look at that little black ring that I told you is inside the transmission, you'll see there's little holes in there, and those holes just create a pulse, and that pulse is telling the board, hey, what's going on? Hey, is it running? Is this still spinning? I turned the motor off, is this still spinning? And that's what this sensor does. So this is part of the shifter, this is the motor here, and this is a sensor. They're two separate circuits, it look like they're two separate things on the machine. They're all one part. Any questions? Okay, so we're gonna stop here because we gotta go over other components in here and testing of these other components and how they work. And then we're gonna do tear down of the transmission, and then we're also gonna do diagnostics from the board. If it takes 2 or 3 more lectures, we'll break it down in little pieces so you guys can absorb it. Because if I talk for 4 hours, you'll forget what the first thing was I said. Any questions? Okay, I'm gonna leave these parts out. Guys, if you guys we can get like a box and keep everything together so it doesn't get lost. Then we'll go ahead and go over this stuff. Tomorrow, we'll continue part 2. I'm Ms. Z tomorrow.